Hello there. Today we're going to look at leave no context behind efficient infinite context transformers with Infini-attention. So the specific techniques we're going to look at are called Infini-attention, and this is by researchers at Google. So Infini-attention is a promise to scale transformer-based large language models to infinitely long input with bounded memory and computation. That is, of course, since a very long time, a dream of transformer models. Transformer models typically have a limited size context window, and there are good reasons for that. And this paper says, hey, what if we did not do that? What if we didn't have a finite, scrubby, finite attention? What if we could process infinitely long sequences? Now, how do they do that? It's a key component in our proposed approach is a new attention technique dubbed Infini-attention. The Infini-attention incorporates a compressive memory into the vanilla attention mechanism and builds in both masked local attention and long-term linear attention mechanisms in a single transformer block. So Infini-attention has this thing called the compressive memory, and it uses that compressive memory to kind of store old stuff from which you can then retrieve things. So we're going to look at how this technique performs or what it does and go into the details of how it works. We are going to look a little bit at the experiments, but honestly, the experiments, you can already tell right now it's going to perform quite well at long sequences. That's what the experiments are going to show. Now, before we dive in, I just feel like, sometimes I just feel like it's like drawing something out of, I don't know why, but just how about we just draw a recurrent neural network for no reason really in particular. So imagine you have, I don't know, like a piece of data here, and that just goes into some sort of processing thing, right? And that just produces kind of some intermediate value, really. In a recurrent neural network, this is called a hidden state or something like this. You can actually have the multi-layer recurrent neural network, and each of them will produce some sort of a hidden state. And then the next piece of data, sometimes the next word or the next token and so on, will actually be combined with that hidden state, right? And then the next layer combined with that hidden state and so on. And that will output, again, hidden states. So this is how recurrent neural networks work. And we've known them for a long time. And they can actually, consume infinite context, if you will, because each computation they do, they kind of store into that hidden state, and then the next thing accesses that hidden state or incorporates it into the computation in order to produce the next piece of hidden state. And therefore, in a technical sense, the next block that would come over here, technically through this hidden state, can, in theory, have access to all the data that came before it, including all the data like from down here and so on. So while certainly no attention mechanism, no transformer, this is completely different. I sometimes just really like to draw recurrent neural network architectures for no particular reason at all. So now, on a totally unrelated topic, let's discuss this paper. What does it actually do? So this introduces this Infini-attention mechanism. It's a new attention mechanism. Now, just to recall, I've not done this for a long time. Just to recall what the attention mechanism actually is, so we can get at the mechanics very briefly. I have a sequence of tokens, usually in language modeling, and I want to transform that sequence of tokens into a sort of next layer representation. So each of these will be represented by some sort of a vector, and I want to transform them one layer up into vectors, just one step up, and I can do that in multiple layers, and that will represent computation through that. Now, if I were in a classical neural network, I would build a so-called dense layer where each of these would be connected by a weight with each of the lower ones, and those weights would kind of build a weighted sum and followed by a nonlinearity somewhere here, and then that would be this signal, not the attention mechanism. What the attention mechanism does is it computes a thing called queries. So queries, Q, will be some sort of vectors that just essentially tell, these are retrieval keys, if you will. Now, they're called queries, but it's like what you input into a search engine. And it will also produce a set of keys K. Now, both of these will actually be produced from the lower representation here, because you obviously don't have the upper representation yet. So you'll produce a series of keys, and then you'll compute what you would sometimes call the routing or the attention matrix or something like this by building the inner product of each of the queries with each of the keys, which will give you, so then since these are 5 queries, so 5 tokens, it'll give you 5 queries and 5 keys. So that will give you a 5 by 5 matrix, which we usually sometimes call the attention matrix A. So the queries will be here and the keys will be here, and each entry here will describe how well a query matches a given key. Now, the thing about the attention matrix, it is then normalized in a softmax operation across the whole space of the keys, and therefore for each output position you kind of get a weighted sum. And you might have heard that before, because I just said a dense layer, a classic neural network, would be a weighted sum. Well, what's different here? What's different is the weighting of the sum of these connections are computed dynamically given matrix A. And in a classic neural network, they are statically learned as parameters of the connection. So we get this routing matrix A, we put softmax on them, and then we aggregate the actual values of the tokens. I said these are embeddings. We aggregate these in a weighted sum that is dynamically computed from these to produce this value right here. In a mathematical sense, we usually represent this like so. Where do we have that? We can just write it down. So we have signal X, and we produce queries. Queries are going to be some sort of function of X, usually some WQ times X, some maybe linear function or some small neural network producing the queries. The same goes for the keys. Using the same input signal will produce keys, and by the way, the same goes for the values, like so. So we've produced queries, keys, and values from the same data, sometimes from different data. Queries can sometimes come from different data than keys and values. But in any case, then we're going to compute the outer product between queries and keys. And of that, we're going to take the softmax, row or column wise, whichever one the keys are, and then that we're going to multiply it by the values. So you can see this here will be, so the inner part here will be this matrix A I've described before, and the outer part will actually be the full routing, like the way to, in a weighted sense, aggregate V for the next layer's X. So that will be XL plus 1. The next layer's X will be that. That's classic attention. Now, as you can see, the big part here is building this matrix right here. For 5 tokens, we already had a memory consumption of 25. And the longer you make these sequences, this goes up quadratically. And that is a problem. And therefore, current attention mechanisms kind of max out at a couple of 1,000 tokens length. Because if you think of, 1,000 tokens, that's already 1,000,000 entries in that matrix. Now, a lot of things have been tried over the years to get that down, but none of them have been really, really successful. So why is it hard to get that down? Shouldn't we be able to do some linear algebra trick? And the answer is no. And the reason the answer is no is because of this softmax right here. This softmax, this kind of normalization step, is really needs a globally available A. Now, there are techniques to kind of do it row by row, right? Because the softmax is across a row. Do it row by row, in which case you're just trading off computation against memory. But still, you have that quadratic complexity in computation then, no matter how you distribute it. There are attempts to do what's called linear attention. So the easiest form of that is you just say, how about I just multiply Q and K, and then I just multiply it by V, and that's it, right? And that's called linear attention. It's also called fast weights. It's also called, I invented transformers in the 90s. It is really like it doesn't really work except for very simple tasks because everything's linear. You can actually even split this up into, you can like then split this up. This is essentially like X multiplied by itself a bunch of times with a few weighting factors. And yeah, doesn't really do too much. So stuff like this has been proposed. Then we've had a whole bunch of things where people just slap nonlinearities on these things, right? They just say, well, if we just have the correct nonlinearity on Q and the correct nonlinearity on K, we can kind of decompose that. And then there are a bunch of kernel papers across that. I think, you know, remembering back, I did a lot of papers on sort of linear and linearish transformers, like trying to get around this quadratic bottleneck. I think this particular one is either the reformer or the performer that said, well, since this is kind of an inner product right here in some space, there should be some kernel or some kernelization trick where in another space it's actually a true inner product. So if we just find this function that transforms it into that space, we can essentially, by sort of RHKS equivalency math that I don't understand, we should be able to do the same thing, right? Like that should be equivalent, but it's not. And the reformer and performer, they suck too. So a lot of things have been tried right here, and Infini-attention is kind of doing that a little bit. The other thing that has been tried, and that's something they compare extensively here, is something like Transformer XL. Now, Transformer XL does a bit of a different take. They say, hey, if we have a long sequence, okay, why don't we just split it up? Here is a segment, and then here is a segment of boundary. Okay, 3 segments. How about we just do attention here? We'll have quadratic complexity, and then the final kind of attention states, we'll sort of leave these, and then the next segment here can kind of also attend to that. Like they can do attention. The queries can also go in here. However, they didn't really have training. They just kind of through the last state in here, and then these could access this state right here. And that was, I think that worked for some stuff, but it's not really satisfactory because you just kind of learning to attend to something. There's not really a planned, okay, what do we actually pass forward and so on. And therefore it was more of a hack and so on. But a lot of things have come up over the years, so let's look at actually how Infini-attention does this. This is the core of their attention. So like the Transformer XL, their attention mechanism consists of 2 parts. One part that does really regular attention. So if you cannot read this too well, it says causal scaled dot product attention and PE. Not sure what. Position embeddings. Okay, position embeddings. So this is regular old attention. Okay. So you have your queries and your keys and your values, and these go in here. Now, this here is also, this is multi-head attention. If you don't know what that is, I've done, I think in attention is all you need. It's discussed. And then a second part, right? The part over here. Now, ultimately, you can see these are added together. So the signal from here is augmented by a signal from here. In fact, it's a weighted sum. So in fact, there's a hyperparameter beta, or a parameter that can even be learned during training, beta, that is how much you trade off the two. So to the normal signal, we also get this side signal right here, and that's supposed to represent data coming from the compressive memory. And the compressive memory is supposed to contain all the information from the past. So we're going to try to, as we go along through these chunks, we're going to try to build up this memory so that when we do attention using the queries, we can look at the current sequence. That's what attention here is doing. But using the same queries, we can also look back into that memory. So how does that work? Well, we have to build up. First, we have to build up that memory. So that's one part of this paper. And second, we have to actually retrieve from that memory. That's the other part of that paper, or of this paper. All right. So the naive approach, we can maybe deal with the naive approach first and then see how the paper actually does it. If you wanted to do this, right? Let's assume you wanted to do this. Here you can see how could you do that, right? Could you just use Q to attend to something? Well, what you would need is you would need sort of a compressed key space of the past and compressed values separately, because keys are first multiplied by queries, then there is a softmax, and then they're multiplied by values. So you can't just use Q and go somewhere and multiply it with something and then expect to get something out of that. You actually need these two things separately because there is a nonlinearity in the middle. Now, that's the reason. So if you want to build up a memory, then you better build up a memory of keys and a memory of corresponding values. However, that is incredibly tricky because you somehow need to store individual values and corresponding keys to retrieve them from. And what you actually want to do is you actually want like something where you can push more and more and more data in, and that something is a matrix. This is very related. What they're doing here is very related to the concept of like an associative memory, and it works a bit like this. Okay, there's a matrix M. Now I want to remember a vector V. So what do I do? I define a key for that V, like K. Okay. Now what I'm going to do is I'm going to do the outer product V times K transposed, right? V is maybe a vector like this, K is a vector like this. I do V times K transpose, which will give me a rank 1 matrix. Okay. Now I have M right here, that's of the same size, and then I do plus. I add those things together, and that gives me M prime. Okay, now let's think what happens. M prime is like M plus V times K outer product. Now, there is an assumption, and the assumption is that the things I want to store, the V's, are generally, and the K's, these things are generally, because they're high dimensional, they're generally kind of orthogonal to each other. And that is actually quite likely in high dimensions, that things are orthogonal to each other, right? If you have 1,000 vectors in a 8,000 dimensional space, that is one empty space. Even if you actually have more stuff, that is, huge empty space, and things tend to be rather orthogonal to each other in high dimensions. So if I now store something else, I want to store, V2, and I define key K2. I define any key, right? Any key by which I want to retrieve that value, and I add that again, and I get M prime prime. So M prime prime is now is M plus key value key V, or M plus vkt plus v2 k2t. Now, when I want to retrieve something, I go with the same key. So here I come and I come with the key k. Okay, so that's this key right here. Now look what happens. I multiply that by m prime prime. Okay, cool. That's m. That's k times m plus, well, let's actually multiply from the right because I totally thought ahead. M prime prime k is equal to m k plus v kt k plus v2 k2 t k, right? So this k is this k and this k, but here only this k. Oh, and this one. No! This one. Now, let's say m can always be decomposed as rank 1 decompositions of some kind. We're assuming they're generally orthogonal, right? We can also just say, hey, we start with an empty matrix or a unity matrix or something, so this falls away. But also consider this here. Since we assume things are generally orthogonal, the inner product now, see, this is an outer product, and then this is an inner product. The inner product between k2 and k is going to be 0, and therefore this falls away. Whereas, because, and we can also normalize them, right? This here, the inner product between the same vector, if it's normalized, is 1. And therefore, this whole thing results in v. So I build up this memory and stored stuff in it using these keys, which I defined, for given values. And then when I go and I added to the same matrix, right? I add these things together, plus, 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 plus. And when I come back and I come with the same key, the likelihood that I'm going to get the same vector, obviously, the more I store, the less precise this gets and so on. But I come with the key to this big memory and I get out approximately that vector again. So we're going to do very, very similar principle here to build up this compressive memory of the past. And that is going to be this part right here. And retrieve is largely going to be how I just said. We go with the same or similar keys or in this case, we come with queries, that we want to grab out stuff, but similar concept. All right. Now, how does this ultimately work? And it works pretty much like I just said. So here is the normal attention. They call this dot attention, softmax of k times values. Compressive memory, on the other hand, is how we retrieve. So first they show us how they retrieve. As you can see, they take the query and they go through some nonlinearity right here, and they multiply that by this memory, and that becomes a mem. And ultimately their output. Now, don't let them confuse you. Regular transformer papers will call A, like I did, the matrix of the attention values, right? Not here. This is actually the output. So this is already multiplied by V, and you can see that up here, where the A is already the output. Usually one will call this here A, but this paper calls A the actual output, which then goes into a dense layer to compute the actual layer output. So sometimes the attention mechanism is followed by a dense layer. All right. So you see there is this memory component and this dot attention component, and they're mixed by this parameter sigma. That's a learned gating scalar. All right, so we have neared ourselves the technique right here. This mem thing just comes about by multiplying a function of q with this m. Okay. So this is in a sense, an associative memory like we saw before, right? So we go with queries and we grab out signal. Now that signal, how is that actually built up? It's built up like this. You may be familiar with that, but here is how we update the memory. We update the memory by taking the last memory and adding something to it. What do we add to it? Well, we add to it a multiplication of a function of the keys and the values, right? And in fact, we'll first do that. So what happens if I retrieve? They don't write it out right here, but what happens if I combine these two formulas? So you can see if I actually replace from down this, and I just pretend up here this is actually ms from, or no, let's do ms minus 1. This is actually equal to, I'll leave the bottom part away, that's just normalization. So some function of q times some function of k times the value plus even the lesser memory, right? And well, would you look at that? It's exactly what we've seen before from these whole linear attention literature. So this here is this is supposed to approximate like the softmax attention in some sense. It's an inner product between two things. It's not a combined softmax. And past literature has shown that approximating softmax like this isn't really super duper viable, at least as far as I know. So this is just linearly combining all of these things together, right? No matter whether that's a non-linearity here, like that's fine, but the point is like the computation itself is completely linear. It relies on this fact that, oh, in some space, this is going to, like, for the correct non-linearity here, this is going to approximate softmax. In fact, if I remember correctly, softmax cannot be perfectly replaced by this unless you go to infinite dimensional space with your sigma function, which you can't do. So yeah, it was a bit weird to me because all you see again is this again and again and again the same principles. If you actually multiply it out, this is just a technique that we've seen before from linear attention papers, just rebranded, and now we're accumulating it in a memory like we're accumulating a bunch of these, but it doesn't change the fact. So they're just using the queries and keys they compute from the attention mechanism, the regular attention mechanism, and they're using the current queries to go and retrieve of a compressed version of all the past key value combinations like this, and rely on this. Oh, if we choose a good non-linearity here, it kind of sort of approximates a softmax right here. I personally would be skeptical. This trick is fairly neat. This inspired by some previous work. They don't actually save like this. When they store like this. So if you multiply it out right here, what you actually add to the memory is this sigma kv minus sigma k ms minus 1. So first you actually want to use the keys. Remember, you see the difference between the formula here, which is sigma q m, and the formula here, which is sigma km. So this is almost like you use the keys as queries to retrieve from the memory. And why do you do that? Well, because this here is what you want to store now in the memory. All of this you want to add to the memory. So what is this? This is what you want to store currently. But first you're going to look up if you have stored that in the past. Because if you have stored the same thing in the past, you don't want to store it twice. So that's why they first retrieve from the memory this part right here, so they can subtract it so they don't store something twice. So they only store the same thing once. That's pretty neat, and keeps the memory less cluttered in a sense. All right, so that's essentially it. So now we've figured out how they store stuff by doing an associative memory like this, how they retrieve stuff by using the queries with the associative memory, and how does that flow into the attention mechanism. It flows into the attention mechanism by means of a linear attention mechanism. So not only does this compress the whole past, it also uses a linear attention mechanism to then include it into the attention. And I somehow feel only one of those two tricks would actually do the trick of infinite length attention. Maybe not infinite. The linear attention is not infinite, okay, but also what you can get with a compressive memory is probably not infinite. Now, how does that all fit together in a model? So here they see what they're doing. So they are taking a segment right here. They're going through layers of computation, and in each layer they're producing this thing right here. Now this is this memory that we've talked about, like some intermediate thing that the next segment can attend to, and in fact will attend to, using its Q values, and will attend to in this linear attention fashion. So this is the diagram of the new novel Infini-attention mechanism that allows transformers to become for infinite attention. This is a new architecture that has been newly invented and is novel, and has certainly not been seen before. And it's the whole concept, in fact, is new. And yeah, and they compare it to Transformer XL, which you actually can't see because of the settings of the iPad, I think. But here they show there's a crucial difference, because Transformer XL, by the way it's doing things, it can only attend like in a stepwise fashion. That means you can only look back few entries into the past from any given layer. So yeah, interesting stuff. All right, so I feel like we've gone through the architecture a little bit. I hope that was at least somewhat clear. They have to put everything into an associative memory, because that's something you can add on top and top and top and top and top. However, because they have to put it into an associative memory, they have to somehow decouple the keys from the query and put the keys and the values together into one thing. And that just doesn't work, because there should be a softmax around the queries and the keys. And you can do this trick where you say, well, if we have the correct nonlinearities on both ends, like here and here, then that kind of approximates, if we have the correct one, that kind of approximates a softmax. And yeah, I'll leave it to past literature whether that is actually true and worthwhile. I personally would be quite skeptical of this method, but I'm absolutely open to believing that it works. Right. They do some tests. I don't want to go too much into the experiments right here. I'm very sure the experiments show fabulous performance on long context tasks, And the related work does mention some stuff, but I think the word recurrent is even mentioned once, but in a some context. So I don't know. Everyone. You tell me what you think. Again, I'm super open to believing that this actually does work and this is the way to go for infinite attention, but I'm very skeptical. For one, it uses linearized attention mechanisms that in the past just have not turned out to deliver on their promises. Second, because it kind of uses this compressive memory approach where you just kind of store as you go along. You don't really learn how to store. You just store in a deterministic fashion, which also means you have very little control over what you store and how you store it. There's just a predefined formula that everything that happens just goes like this into the memory. And even the retrieval, you can't really help it, so to say, but to retrieve in that one way they give to you. You cannot go back into that infinite context and, to a fine check and anything like this. So that makes me doubt that, because you would essentially have to very selectively store stuff once you get into the really long context game, right? You can't just compress equally the past into such a small state. And lastly, because it's essentially a recurrent neural network without the benefits of the recurrent neural network, which is a back propagation through time so that it actually actively learns what to remember. So it gets the drawbacks of recurrent neural networks, which is everything has to go through that one hidden state in the middle without the benefits. And all of these things kind of combined make me doubtful. On the other hand, I am super happy that people are trying out new stuff into very long attention, even infinite attention, and so on. Make up your own minds. I'll leave a link to the paper in the description. Tell me what you think and stay hydrated. Bye bye.